Similar to when we did force of gravity, we can also look at cases of collinear problems involving gravitational field strength. The big thing that gets students with these problems is they mix up gravitational field strength and force of gravity. They're similar and they're related, but they're not quite the same, because we know that difference between them is that factor of m, because we know that Fg is equal to m times g. So we want to find the net gravitational field strength at point P produced by these two masses below. So what makes these problems a little bit different than force of gravity problems is at point P we don't have a mass there, as in the sense that like in the previous problems we might have had like an actual mass here. It said like find the force of gravity on this mass. This time there's no mass here. We don't have anything mass here wise here, but what we're going to say is we're going to pretend we're going to place a test mass here, because the idea behind gravitational field strength is if we placed any object here regardless of its mass, what's the acceleration it's going to feel, or as we mentioned, the other proper phrasing for that is gravitational field strength. So the first thing we want to do is we want to still draw a free body diagram. And when we draw our FBD, we're still drawing it from the perspective of forces, because we can still talk about having a pretend test mass here, at point P, and we can still ask the question, what's happening to that test mass because of the other two masses. So I'm going to call this first mass M1. I'm going to call this second one M2. So I could say because of this first mass here, there's a force of gravity pulling on this to the left. So we could say that there's an F, we'll call it an F1. At the same time, this second mass, it's bigger and it's closer. It would also attract a test mass towards it. So we could say that, there's a force 2 going that way. What we know is that the direction of the net force is going to the left here. The direction of the net force is going to be the direction of our gravitational field strength. So we know that G is also going to be directed that way. What this means is I'm also going to call left to be positive. So for these problems here, all I have to do is find the gravitational field strength, or the contribution to the gravitational field strength for each object. So I'd find the gravitational field strength because of this first mass, ignoring the second one. Then I'd find the gravitational field strength at this point due to this mass, ignoring the first one. And then because they're both trying to pull this test mass towards them, we're going to add them together. So we can say that the total gravitational field strength, it's just the gravitational field strength on object 1 plus the gravitational field strength on object 2. And then of course we have definitions for these. So we know gravitational field strength is gm over r squared, and we're just going to write that here. Now, since they're going in the same direction, we don't have to worry about any sign issues. If you want to calculate G1 and G2 separately, that's perfectly fine too. That's also a great strategy. So the only thing we have to be a little bit careful with is the radii, or the r values. So R2 is that distance between the point in question and the center of mass 2. So we're told that R2 is 2.25 meters. The only one we got to watch out for is R1, because people are going to see that 2.50. But remember, we want the total distance between the center of that mass and point P. So we actually need 2.50 plus 2.25. So the total distance for R1 is going to be 4.75 meters. So at this point, we pretty much have everything ready to go. So we can start to calculate the total gravitational field strength. So we're going to put in our contribution from the first mass here. And we're just going to put this 4.75 meters. Again, don't forget the square here, always a common mistake. And then we're going to add on that contribution of the second mass here. And it has a mass of 30 kilos, and it's only 2.25 meters from the point. And again, don't forget that square. So we've got a lot of terms here. So again, we've got to be really careful with our addition in the calculator and all the key work. So we're just going to enter this in really nice and slow. And then if I'm really careful with my keystroke addition, I'm going to get something like about 4.54 times 10 to the minus 10 newtons per kilogram. Now, let's put this answer into context for a second. I'll deal with direction in a moment because I'm not quite done with this. So this 4.54 times 10 to the minus 10 newtons per kilogram, what this means is if we had this exact layout here, like we had a 20 kilogram mass and then 2.50 meters away we had a 30 kilogram mass, and then 2.25 meters away from that we had any mass. It could be you, me, doesn't really matter. What it's saying is an object placed at that point, it will accelerate towards these two bodies at a rate of about 4.54 times 10 to the minus 10 meters per second squared. As we've mentioned, acceleration due to gravity, it's only going to be significant when we deal with large masses. Tiny masses, not going to do much in that way. So for direction, I don't really have any indication of what the direction is, so I guess all I can really say is towards the left. So we're going to say that the net gravitational field strength is about 4.54 times 10 to the minus 10 newtons per kilogram. And then we're just going to say left. On exams, you may have more specific prompts like a direction, but left works fine for us.